Hi, I'm Ajay Badita, a PhD student in the Department of Electrical Communication Engineering in University of Science, Bangalore. I'm being advised by Professor Parmal Parag. This is joint work with Banita, who is a professor at Purdue University. This talk is about common problem in large-scale distributed systems. When we are doing the parallel computation of the job completion time is limited by slowest server, which we call the straggler. One way to mitigate these stragglers is to have redundancy of subtasks, but this could have an impact of server utilization cost. Here, we propose a solution which takes advantage of redundancy and at the same time, it deals with the cost as well. Distributed computing uses multiple distributed servers to process the job where a job is divided into subtasks and each launched on a single server. The execution of a task on a machine has stochastic variations due to many contributing factors such as co-hosting, virtualization, hardware, and network variations. Considering this randomization, we assume that the service completion times at each server is a random variable and are IID in nature. When a job is divided into six subtasks and assigned each onto a unique server, the completion time of a job is the largest completion time among all six server completion times. The problem with this setup is that slowest subtasks are determining the job execution time, and these slowest subtasks are called stragglers. Some of the examples of use cases are here. In the setup shown at the right, we consider MDS coded redundancy where subtasks are encoded to more number of coded subtasks, and each server is working on a unique coded subtask. Completion at any 6 out of these 10 results in completion of the original job. As soon as 6 coded subtasks are killed, the remaining servers, as soon as 6 coded subtasks are completed, the remaining servers are killed. This redundancy method guarantees us in lowering the completion time by mitigating the stragglers, but is more expensive because maximum number of servers that were in use here are 10. In order to decrease the cost, one can think of delayed relaunch of servers. In delayed relaunch scheme, instead of starting all the servers in the beginning, we're going to add the servers in multiple stages. Instead of starting from 6, as in the no redundancy version, or starting from all 10, like in previous slide, here we start with arbitrary number of servers and then we will add the remaining servers in later stage. The design choices here are how many servers to start with and when should I add the remaining servers. The first one is called choice of initial servers and the second one is called choice of forking time. One way to take care of this forking time is you add the remaining servers when certain number of tasks are completed. This number of subtasks required to add remaining servers is called fork task threshold. We have to decide in a way that how should the parameters, initial number of servers and fork task threshold be chosen so that both the metrics, service completion time and server utilization cost are optimized. Let's consider an example of 10 total servers, 6 subtasks coded to MDS, 10 coded MDS subtask so that once we get any 6 of them, we can enter computation. Here, initial number of servers that we choose are 7 and we will start adding the rest of the 3 servers when 2 of the initial 7 complete. Stage 0 is from the beginning of 7 servers till 2 complete and stage 1 is from the point of 2 completions till 6 complete. The completion time is the sum of inter-service completion times of stage 0 and stage 1. The first 2 terms are coming from stage 0 and the last 4 terms are coming from stage 1. It is clear that to compute the means of the performance metrics, we have to compute the mean of inter-service completion times. Here we plot the trade-off between mean server utilization cost and mean completion time for different values of initial servers. For the case where initial number of servers are always greater than the required number of cores of tasks 12. As you see that when initial number of servers increase, the mean job completion time decreases by trading it off with the mean utilization cost. But this flexibility is not there when we fix the initial number of servers. We find out that in order to get a good trade-off point, choice of initial servers really matters. We implemented this setup for Intel DevCloud compute cluster. We observed that empirical distribution of core subtask execution times at each node has characteristics of shifted exponential distribution. Using quantile plots, we verified that the shifted exponential is a good fit for the empirical distribution of execution times. We empirically verified that the performance of two forking is same as that of single forking. In summary, for an MDS coded subtask, we analyzed delayed relaunch scheme with single forking. We analytically computed the mean service completion time and mean server utilization cost with shifted exponential service times and studied the effect of initial servers and fork toss threshold on the two metrics. Insights obtained hold true on real-time compute cluster and also hold true for heavy tail distributions like Pareto and Bible. And we found out that the choice of initial servers really matters. Thank you.